Hi guys, welcome to lesson 2 of the acid-base series. In this lesson we're going to talk strictly about buffering in response to acid-base imbalances, and then in the next lecture we'll talk about compensatory responses. Okay? Before we get into that, we need to talk about the Henderson-Hasselbalch equation. Now in the last lesson we talked a lot about this carbonic acid equation, or carbonic anhydrase equation if you wish to put it that way, since carbonic anhydrase typically catalyzes it. In that lesson, for instance, we talked about the fact that if you increase carbon dioxide, you shift this equation to the right and you produce bicarbonate and you produce hydrogen ions, and the pH goes down. pH goes down, hydrogen ions go up, okay? But what we didn't address is the how much part of that. In other words, that's a nice qualitative explanation of what's going on, but quantitatively it doesn't tell us how much does the pH shift, how much does bicarbonate go up. And we're going to talk a lot in this lesson about that. So the answers to that question start with the Henderson-Hasselbalch equation. That is this equation here. And what it does is it characterizes changes in PCO2, hydrogen ion concentration, and bicarbonate numerically. So here we have pH equals 6.1 times the log of the bicarbonate concentration divided by the partial pressure of carbon dioxide. Okay, and that is the equation, and you should memorize it so that you can do the calculation. And you should note that given any two of these parameters, for instance, certainly given the bicarb and the PCO2, you should be able to calculate pH. But given any of these two, you should be able to calculate the other. Given pH and given bicarb, you should be able to calculate PCO2. Given pH and PCO2, you should be able to calculate bicarb, okay? So what that means is that we can construct a graphical relationship between these three parameters. And when we do that, it's called the Davenport nomogram, okay? This turns out to be fairly complicated because instead of just a relationship between two parameters, x and y, we actually have a third parameter that has to be accounted for here. And you'll see how we do that in a moment. You may ask, why do I have to learn this? The first reason is because it's in the review books, which means you need to know it for step 1. That's the big reason. The second reason, and the reason why it kind of makes sense, is that if you understand this graph the way that we're going to construct it, you're going to be well on your way to understanding pretty much everything you need to know about acid-base, at least in terms of the physiology. So we're going to concentrate a lot on this graph as we walk through some of the physiology behind these acid-base changes, okay? So the first thing you'll notice about this graph, we have bicarb on the y-axis. We have pH on the x-axis, okay? We are missing a variable, and that is the partial pressure of carbon dioxide, okay? So because we have a third parameter to account for here, what we do is we add what are called isobars to the graph. And this is the isobar representing these relationships when the PCO2 is 40 millimeters of mercury, and that is the normal PCO2, okay? So you will note that this isobar, the blue line, goes through the origin of this graph. And that means when our PCO2 is normal, 40, and our bicarb is normal, 24 millimolar, we have a pH of 7.4. And that is actually, we make that the origin of the graph to make things simple, all right? And all this isobar is the relationship between bicarbonate and pH at 40 millimeters of mercury PCO2. So if I'm at 40 millimeters of mercury PCO2 and my bicarb is at 16, my pH is roughly 7.2. And you can actually look at that and see that on the graph. okay? So you can do that for any bicarb concentration or any pH where you want to know the bicarb. You can just go up and down this line, all right? Now, the same thing goes for other values of PCO2. For instance, if my PCO2 is 60 millimeters of mercury, now my relationship goes along the red line, all right? So at 60 millimeters of mercury CO2 and at a normal bicarb, our pH is down. Once again, it's about 7.2, a little bit, maybe a little bit to the left of that, but pretty close, or a little bit to the right of that, so, but pretty close. And that should make sense to you. If you look at your carbonic acid equation, high CO2 shoves that equation to the right, and if bicarb is the same value, it should make sense to you that your hydrogen ion concentration should be up and your pH should be down. And that's what this represents right here, all right? Okay. On the other hand, if my CO2 is down, let's say instead of 40, it's 30, now I have a new isobar here. And my relationship between bicarbonate and pH varies along this line. So if I have normal pH and my PCO2 is 30, I can look over here and I can see what the bicarb should be. It should be about 18, okay? And bicarb of 18, PCO2 of 30, if you plug that into this equation, you get a pH of 7.4, all right? So that's how this works, and naturally enough, this holds for any PCO2. You can draw isobars for any PCO2. We have them here for 10, 20, 30, 40, 60, 80, and 100. All right, so our Davenport nomogram has a bunch of isobars representing CO2, so that if we can look at the relationship between bicarbonate, pH, and CO2 all in one graph. Okay? All right. So, having said that, let's talk about what happens when we add a buffer, a strong acid, an acid to our system. Okay? And this would be a non-carbonic acid, and we would actually call this a metabolic acidosis. It is a non-respiratory acidosis because it's caused by something other than carbon dioxide, okay? And and it's caused by something other than a lack of bicarb, because that is also part of the non-carbonic acid system. So this is acid that's not part of that system, something like lactic acid, okay? So let's say this is lactic acid and we add it, all right? Let's talk our way through this. So first, our hydrogen ion, our added hydrogen ion, our added acid, lactate, dissociates into a hydrogen ion and a non-carbonic anion. If this were lactic acid, this NC would be lactate. It would dissociate into hydrogen ions and lactate anions, okay? All right, so that's the first thing that happens, all right? Now, our plasma hydrogen ion increases, and as that increases, our bicarb reacts with it and shoves our carbonic acid equation to the left. Okay, so what happens as the hydrogen ion goes up in response to the added acid? Bicarbonate disappears and it goes down. Okay. Now notice we're talking about before compensatory responses kick in. All right, so there's no change in respiration in response to this yet. All right, we're just talking about buffers. And you'll also notice that despite the fact that I'm producing more CO2 by adding hydrogen ion over here, that my partial pressure of carbon dioxide doesn't change. And that's because when my plasma enters my lungs, my carbon dioxide equilibrates with my alveoli. And unless the carbon dioxide in my alveoli change through something like a change in respiration, my partial pressure of carbon dioxide in my blood doesn't change. In other words, my my respiratory system naturally gets rid of the extra carbon dioxide simply through equilibration with the air and equilibration with the alveoli, which is a large sink for carbon dioxide, okay? So despite the fact that I'm producing more here through this reaction, this partial pressure doesn't change. So the partial pressure of carbon dioxide is constant here, but my bicarb is not. It's going down, all right? So let's see what this means. Here's my Davenport nomogram, all right? I'm starting at a PCO2 of 40, which is normal, and I'm adding a non-carbonic acid, okay? And that non-carbonic acid adds more hydrogen ions, shifts this equation to the left, and my bicarb goes down. So how do I represent that here? Well, my CO2 is not changing. So I'm going down along this 40 line because it's being held constant, but my bicarb is dropping. So as my bicarb drops, I go down along my green line, and I can see that my pH is dropping along with it. So I have a drop in pH, an increase in hydrogen ions, and I have a drop in bicarb as this bicarb disappears, okay? So that movement in the Davenport diagram tells you what's happening to bicarb and pH, okay? And how far you go down in pH depends upon how far you go down in bicarb. The more hydrogen ion you generate, the more the bicarb goes down, and the more you shift down along this isobar, okay? So that would be a metabolic acidosis. The addition of a non-carbonic acid, let's say the addition of lactic acid, would do this, okay? All right, that's without the compensatory response, which we're not talking about right now. All right? The same thing happens if you add base to the system, which would mean you're making hydrogen ions disappear. Now, my hydrogen ions are going down because they're binding to the added base. And now, as my hydrogen ions go down, my carbonic acid equation is shifted to the right, and I produce bicarbonate. So I go up along this isobar, okay? My bicarb goes up, my pH goes up because my hydrogen ion concentration is dropping. That's our representation. And notice that this doesn't just hold true for a PCO2 of 40. You can use any of these isobars depending on what the PCO2 is. For instance, I could have a PCO2 of 60, okay? So if my PCO2 is 60, now I'm moving along this isobar, this 60 millimeter of mercury isobar. And if I add base to the system to bring the hydrogen ion concentration down and increase the pH, because you'll notice the pH is low here. If I add a base to increase the pH, I drop my hydrogen ion concentration, my pH goes up, bicarbonate is added to the system as I shift my equation from left to right, and bicarb goes up. Bicarb goes up that way, pH goes up that way, bicarb goes up this way, and we move along this black line. So it doesn't just work at 40, it works along any isobar, okay, depending on what the PCO2 is, all right? All right. So that's going to be the end of the first video where we introduced you to the Henderson-Hasselbalch equation and the Davenport diagram. In the second video, we're going to do respiratory acidosis, which is a little more complicated, but we're going to do the same thing with the Davenport diagram. And then in the third video, we'll talk about the anion gap again. All right? Thank you.